Guys, this is the second part of our 15.3 lesson on double integrals over general regions. Hopefully, if you're watching this right now, you've already checked out the first video and have the basic gist of how these work out. So let's go ahead and get some examples in. Wanted to start out with a couple more of the type 1 integrals. Those are going to be the more familiar ones because we're dealing with functions of x rather than functions of y. But at any rate, here's our example. We're trying to evaluate this integral of x with respect to area. I'm specifying to evaluate this as a type 1 integral where the region in question is going to be a disk of radius 4 centered at the origin. So, just to clarify here, circle, disk, same thing. We'll pretend that this is a circle. Radius 4 centered at the origin. If I'm trying to interpret this guy as a type 1 integral, ideally what I want is for there to be bounds on y that are functions of x, and functions of x pass the vertical line test. That means I want to break this up into this as being some sort of top bounding curve, and this guy down here is being some sort of bottom bounding curve. Those would be my bounds on y, and then hopefully after that we can worry about what sort of numerical bounds I end up having on x. Okay, now for me to get this, I didn't outright give us what these functions were that bound y, so we have to kind of come up with that, right? If I'm worried about my bounds on y here, start with the circle equation. We hopefully recognize that you're going to get something like x squared plus y squared at the beginning of your circle equation because we're centered at the origin. This should be equal to the radius squared. Our radius is 4, so this should come out to 16. Now, as far as turning this thing into actual functions that will bound y, I'm going to go ahead and solve for y to get those functions of x. What this is going to give me is that y squared is equal to 16 minus x squared, or, let me scroll down and give myself a little bit of room here, if you square root both sides, you are going to get the plus or minus square root of 16 minus x squared. Okay, so notice we've got both a plus and a minus in the solution. Please don't forget that when you root things, you get both of those. And the fact that we're giving both, well, that's where your top branch and your bottom branch of these equations are going to be. So hopefully it should be pretty clear which one's on top, which one's on the bottom, so which one's the larger value and which one's the smaller value. So these will serve as our bounds on y right here. And if I'm worried about my bounds on x, well, let's think about this. I've got a circle of radius 4. I've already marked out what the furthest we can go towards the right in the x direction is. Hopefully it should be pretty clear that the furthest we can go off to the left is going to be minus 4, right? So I'll go with minus 4 to 4 as that collection of bounds. Now I have enough information to set up this integral of x as a type 1 integral. I'll go ahead and scroll down and set this up here. We hopefully recognize if we're doing type 1 integrals, numerical bounds have to go on the outside. My function bounds have to go on the inside. The smaller one goes on the bottom, so this is going to be my minus root 16 minus x squared. And the one on top is going to be my 16 minus x squared, the positive version. And the integral that I'd ask you guys to take was of the function x. Now remember, we have to match whatever my dy dx, dx dy is to my bounds. Those outer bounds were bounds on x. That means x has to go on the outside and y has to go on the inside. Your type 1 integrals always have you integrating with respect to y first. At this point, I can go ahead and start evaluating. Again, evaluation works like double integrals in our previous section. You start from the inside and you work your way out, which means that right now these outside things, they are really not doing very much, so we're just going to hang on to them. I do have to take an antiderivative of x with respect to y, x acts like a constant, so my antiderivative is just xy. And this has to be evaluated between my bounds of y equals negative root 16 minus x squared and y equals positive root 16 minus x squared. Okay? Now, if I'm setting this up, the next step is we actually should evaluate at these bounds. So I have to plug both of these things in for y. I will get an x times this top thing that I have to plug in, so an x times that root. And then I'll have to subtract off what happens when I plug in the bottom. Well, x times this negative will give me a negative value. That I'm subtracting off. So those signs are going to cancel. I'm ultimately going to be adding another copy of this x times root 16 minus x squared. Now, I could work with this thing as is with both of these terms to simplify this, but I would rather not do that. It's probably a little bit easier if I combine all of my like terms so I have less stuff to integrate. You notice I have 2 copies of this thing, so I may as well denote that with a coefficient. And you may notice that when I did that, I set myself up perfectly for a u substitution here. Okay, this is now just a straight up calculus 1 problem, just a regular single variable integral, which we can treat with u substitution because of that composition in the middle. Okay, so notice I have u is my inside function, 16 minus x squared. That will make my du be minus 2x dx. Or if you want to plug this in a little bit cleaner, you can note that minus du is what you replace that 2x dx with. So that when I go to actually simplify this down into an integral that I can take directly, my integrand is now a square root of u, okay, and the 2x dx, well, that turned into a minus du. Now you have 2 options on how you could proceed from here. Either you could just worry about what the antiderivative is and switch back to x, or you do have the option of fixing your bounds, and you do that by taking your old bounds, which are x values, and substituting them into your u function. Okay, substitute them in for x to get your replacement u. Now a comment here, this is actually kind of a little bit of a trick problem, because if I make those substitutions, you know, the upper bound for going in for x, 16 minus 16 ends up being 0. Okay, and kind of the same thing happens with this minus 4. If you plug that in, you're getting a 16 minus a 16. You also have a 0 as your lower bound. I could actually sit here and work out my antiderivative and evaluate everything out, or I could remember a fast trick from Calculus 1. Since definite integrals are supposed to tell you the area underneath the curve, or the signed area between the curve and the x-axis, you don't get any area over an interval that has length 0. So I'm going to go ahead and shortcut this one. We get a big old 0 back there. Now, a comment in case you were kind of wondering, why did I get 0 back? That's kind of weird. Remember the whole idea of evaluating these double integrals, what they're trying to tell us is you get a feel for signed area between your function and the xy plane. Okay, so I'm going to scroll back up just to take a look at what function we actually were starting with working with on the first place. This is just x. Basically, z equals x is our function. And that was the function that we're dealing with over this disk of radius 4. Now, a comment geometrically if you want to get a feel for what's going on. That's a plane. It's probably going to be kind of tricky for me to attempt to draw here. But you've got your z value basically trying to mimic your x value here. So if you think kind of like how in 2D the line y equals x is a big old diagonal, you know, we could kind of get something a lot like that here, except for I'm running all of these parallel lines through the y-axis because y doesn't really have any bearing in that function. So basically what's happening is if you end up integrating over this disk, all of the stuff on this side, okay, you're getting some sort of a wedge which is above the xy plane. And then over here on the back end, you're getting some sort of a wedge which is below the xy plane. If I wanted kind of a side view of this figure, what you're looking at is, here's where your area is negative and here's where your area is positive. They're pretty much exactly canceling each other out, which is why we got 0 here. Okay, so sometimes you'll get positive values, sometimes you get negative. Sometimes 0 is a perfectly valid result for these. Okay, and again, if you missed some of that explanation here, we'll go ahead and move on to our next example. Kind of what I was mentioning before, a lot of what we're finding with these double integrals is volumes, okay? If you go to integrate some sort of function over a region, it is giving you signed volume between that surface and the xy plane, okay? So another thing that we might be interested in learning how to set up is if I just give you a surface and ask you to find some sort of relevant volume, well, can we figure that out, right? So here, in this particular example, I'm going to scroll down a little bit. I'm asking for us to set up an integral for the volume of the region that is between this plane and the xy plane in the first octant. Again, I didn't give much in way of setup here, so I didn't even give you bounding functions. Like last time I gave you, some sort of a region and specified what that region would be that we were interested in. I didn't even do that this time. I'm just telling you this plane in the first octant. Now, if you're iffy on what I mean by octant, there are basically 8 octants in 3 space, based on whether, your x, y, or z components are positive or negative. When I say the first octant, I'm meaning where all of my x, y, and z components are positive. So whenever we go to draw the x, y, z space with this little triad of positive axes, I'm basically talking about all the stuff that lives towards us, okay, if we think of this as us looking at a corner here. Now, as far as getting a feel for this, if you have no clue what it looks like right off the bat, please try to do a sketch to get a feel for what this looks like. You notice when we did sketches of these things before, and it's been a while that we've looked at planes, but when we did sketches of these things before, the trick that we used was to try to look at intercepts, okay? So if I'm looking at intercepts, this becomes me asking the question, if x and y are 0, what's z? Well, in that case, if x and y are 0, z is 6. That means that if x is 0, you go 0 units out on the x-axis and 0 units out on the y. You end up going out 6 in the z direction. And very similarly, I could figure out what's going on with my other axes. If y and z are both 0, you can solve for the fact that 3x is 6. That means that x had to be 2. If both x and z are 0, you're getting back 2y is 6, so you can solve for the fact that y is equal to 3. That's me specifying 3 points that are intercepts on my axes. 3 points should define some sort of a plane. So you notice that when I draw this triangle here, this almost tetrahedron looking thing that I have in the corner, this is the region that I'm trying to get us to find a volume of. Okay, so there's that plane and the xy plane, so the bottom surface of this thing. Basically, I just get to set up an integral of whatever function represents this surface, right? Now, I gave you a plane, I maybe didn't necessarily give you a function. really what I want to do is treat z as f of x, y as usual. We have this interpretation that you plug in some sort of a lateral coordinate and it spits out a height. If it's not given to you in this format, there's nothing that stops us from solving for that, right? So here, if you're worried about this function, solve for z here. This is basically me moving everything over to the right hand side except for the z. So basically, I'm going to scroll down a little bit here. What I'm really looking for is this guy basically to be my f of x, y. Okay? And what I need to do to evaluate the area is you should be able to integrate that function over an appropriate domain, right? So basically, where does your function live that we care about it? We pretty much want to stay within this triangle, because if I go too far back in the x direction, I'm going to catch stuff that's not in the correct octant. Same if I go too far back in the y direction. And if I come too far forward, my plane is starting to dip into negative values. I didn't want to catch any of that. So basically what I'm looking at is if I wanted to treat this region right here as my R, well, I need to find functions and numerical values that describe this region, so I can basically set up my integral of this function f on this region R. Okay? Now, what I'm going to go ahead and do, is get my cat out of the way. Hold on one moment, guys. Is sketch this guy here. She's being very persistent. Sketch this XY plane that I have. And try to keep track of where exactly it is that I have this region, right? You'll notice that I had us going up 3 units in the y direction and 2 units in the x direction, so that that region, which I had shaded red before, this is really now this thing. At the very least, your bounds on x should be pretty clear if I want to set this up as a type 1 region, right? My bounds on x are going to go from 0 to 2. On the other hand, for your bounds on y, well, the bottom one should be pretty clear. Horizontal line, y equals 0. Okay, that's going to be your lower bound. If you're looking for the top function, though, well, note that you've got 2 points. We should be able to figure out a line from this, right? So if I'm worried about my bounds on y, that top line, 1, it has a y-intercept of 3. If I scroll down just a little bit, it should have a slope of, well, slope should be rise over run. This thing has a rise, at least between these 2 points, of -3 and a run of 2. If I take my rise over run, this is going to be -3/2. This means that that top curve is going to be y equals your m times your x, so -3/2 times your x, plus b, so plus your y-intercept, which is 3. Okay? So we've got that, that was our top line. Again, this bottom line is going to be y equals 0. We should be able to pair those bounds on x along with our bounds on y to actually get my volume straight here. Okay, so again, the whole goal was to set up this integral of f over the region that is specified by these bounds that I've marked here, okay? And up here was our function f in the first place. So the function that I'm looking to integrate is 6 minus 3x minus 2y. I'm going to scroll down and give myself some room to write that. So 6 minus 3x minus 2y. This is something that we had to integrate over our region. My bounds on x went from 0 to 2. My bounds on y go from 0 to minus 3 halves x plus 3. And those inner bounds were on y, and those outer bounds were on x. I'm not going to bore the details of the solution of this with you guys because, you know, if we scrolled up and take a look, all I asked for here was just set up. However, if you do want to get some practice on this, you're welcome to try to give this integral a shot. Now, moving on, I had one more that I wanted to tackle in this video for you guys. I've done a lot of type 1 examples thus far. I have not done any type 2 examples, so we're going to go ahead and try one of those. Remember, the difference between type 1 and type 2 integrals was that you have functions of y serving as bounds on x. So instead of seeing, you know, a bunch of expressions in terms of x serving as your inside bounds, we're going to be looking at things that have y's written in my functions. These are going to be my inner bounds. Okay, so in this particular example, I'm going to scroll down and give myself a little bit of room. If I want to evaluate this thing where that's my region in particular, well, never hurts to draw a picture, try to get a feel for what this looks like. Here, if I wanted to sketch these guys, remember the difference between when you have functions of x and functions of y. These basically just look like you took the line y equals x as a mirror and you just flipped the regular function over that mirror, right? So instead of, you know, y equals x squared being a parabola that opens up, if we mirror that, we should get a parabola that opens to the right. And pretty similarly, instead of that kind of almost S-curve that we had with stuff in the first and third quadrant, well, if you mirror stuff in the first and third quadrant over the line y equals x, you still get something in the first and third quadrant. Turns out you're just going to get something that looks a little bit like this guy, so maybe a little bit less angular, but at any rate, the region that we're looking at to integrate over is that little wedge right there. Okay, so that's going to be the region that you're integrating. Now, if you're not so confident about thinking about it geometrically like that, another option that you do have is you could solve for y in both of these equations if possible. You know, y is cube root x. You will get this curve. Y equals plus or minus square root x, you will get both these top and bottom curves. If you plot those, you get your region. If you want to check out geometrically what's going on, you know, double check which function's on the left, which one's on the right, maybe what are these points of intersection actually happening at. The typical way that we go about doing that is to set these things equal and solve for my points of intersection. And then once I have those points of intersection, I can check a test point to figure out what's the larger function. Okay, so I'm going to go ahead and do that. This looks a lot like what we did back in Calculus 2 with finding areas between curves. I will set both of these equal. The whole goal of this is to find my bounds. Right, so if I set these guys equal, well, please don't make the mistake of just trying to divide through or something like that. Usually whenever we're dealing with polynomials, we almost always want to move everything to one side and then see what we can factor out so we don't lose any solutions, right? If you had just divided everything through by y squared, you would have gotten y equals 0, and sure, you would get that root, but you probably would have let this y equals 1 root be missing, okay? So if I'm looking for bounds, at least on y, my numerical bounds are going to go from 0 to 1. So this guy right here, that intersection at the origin, we expected. This thing goes up to 1. Now, as far as maybe figuring out which function's bigger, which function's smaller, if you don't necessarily believe me that the cubic function falls on the left-hand side of that parabola, if you're worried about the larger function, pick some sort of a test point on whatever your interval is. So for example, if I wanted to maybe compare something like x1 when I plug a half in, this is going to be a half cubed, that's an eighth. If I wanted to compare that to x2 when I plug a half in, well, that's going to be a half squared, which is a fourth. That means this guy, x2, this is the larger value. Okay. So, we've got a feel for what my bounds on y are. We've got a feel for which order my bounds on x should go. Okay, so x1's the smaller one. Now we can go ahead and actually set up this integral of xy. Okay, so integral of xy, my numerical bounds go on the outside. We've just said, that x1, which is y cubed was my smaller function, and y squared is the larger one. Okay, and I was trying to integrate xy in the first place, right? So you notice, again, these y values, or the y squared, y cubed, those were bounds on x, and this interval, okay, the interval 0, 1, these were y values too, so these were bounds on y. We're doing a type 2 integral this time, so the order of integration is backwards. The y is on the outside. Now when I go to evaluate this, again, we start from the inside and we work our way out. We'll scroll down and get a little room here, meaning that the outer stuff, we can worry about it later. If you antiderive the inside with respect to x, the y acts like a coefficient, so we just hang on to it. But you actually do antiderive the x part, so get x squared over 2 here. This has to be evaluated between x equals y cubed and x equals y squared. If I go to substitute those things in, the top one has to go in first. So if I plug in y squared first, y squared, oops, sorry about this here, this guy should be an x. If I go to plug in y squared to x first, when you square you get a fourth power. That means it's multiplied by y. I should really get a fifth power there. When I go to plug in the second term for x, well, that means that we have a cubic that we are then squaring. If you take a power to a power, we are multiplying. So that would really be a y to the 6th power. Multiplied by another y, that means I've got a y to the 7th here. Okay. At this point, this is a straight up calculus 1 antiderivative problem. Power rule thrown at this, I will get y to the 6th. Divide this thing by 6, I'll get a over 12. Minus a y to the 8th. If I divide this thing by 8, I'll get that this is over 16. This is evaluated between 0 and 1, which should be pretty easy to substitute in. Basically looks like 1/12 minus 1/16 minus what happens when I plug in 0, which is not a lot. And then from here on out, pretty much the only thing that you would really need to bother doing is figure out some sort of common denominator that will help you combine these things together, right? So probably something like if I try this over 48, this boils down to 4 over 48 minus 3 over 48. Your end result is 1 over 48, okay? So final result for this problem, if I was worried about, based on this setup, my signed area of the function z equals xy over this region, okay, between the cubic function and this square function, end result, we got more positive area than we may have had negative area.